things are going to blow up a little bit here. And we're going to use what we just did in that last section, but there's two parts to the fundamental theorem of calculus. This is the second part, and I would say this is the most important part, one of the biggest theorems you're going to see continually for the rest of this semester, like on and on and on and on. Big time for calculus. So we just saw this notation earlier, a couple assignments ago, the integral from a to b. So what does it mean? So if you find the integral from a to b, we're going to take the antiderivative of f, and we're going to call that capital F, basically. So the way we evaluate the integral, we're going to find algebraically, we'll find the antiderivative of little f to get big F, and then we're going to evaluate that big F at b and subtract it from the evaluation at a. And we're going to do this later on algebraically. There's kind of an introduction. Strange that we'd start here in the introduction. And this is a little notation just telling you that big F, establishing that big F is the antiderivative of little f. Because it's saying if you take the derivative of big F, you end up with little f, right? That just means that if you were to take the antiderivative of little f, the integral of it, you would end up with big F, right? They're just saying that they're antiderivative and derivatives of each other. So let's mix this up with what we just did. Let's just say, for example, I wanted to find the derivative, and we're just going to get a little bit in general here of something. So let's just say I want to find the derivative of this integral. So notice the bound is not just a number and then x. We have a number and then x squared. So it's going to change it up a little bit. So what I'm going to start with is I'm actually going to start with focusing in on this integral. So if I were to rewrite that, that would be big F of x squared minus big F of 10. Right? According to this, we're just finding big F of, big F of x squared minus big F of 10. That's what we're doing with the bounds here, right? We did the antiderivative of little f to get big F. And don't forget, we're still going to derive these. So when I take the derivative, remember, the derivative of big F is little f, isn't it? Now be careful. We now have an inside function, so we're going to have to do the chain rule. So when I take the derivative of big F, it becomes little f, keep the inside the same, and then times the derivative of the inside. So I had to do the chain rule here. So what does this represent? This here represents our original function. Whatever was inside the integral, f of, just instead our x got replaced with an x squared. So whatever our original function is, we're just going to take the x and replace it with an x squared. And then we're going to take that whole function, whatever it is, and multiply it by 2x. That's what this is saying. Then when we take the derivative f of 10 is just some number, so its derivative is 0. So final answer. But here it's the concept, the idea that this represents the original function here with an x squared plugged in. Just like we did in the last one. Remember the last one, we plugged in an x, right? We just took whatever was in this function, we plugged in an x. And I guess I kind of messed up here. I should have done f of t dt, right? Technically. Now check this out. And I don't think we have this in this assignment, but I've seen this on AP. Very rare, but they might ask it. What if our bounds both had x's? Then when we evaluate this, we would have big F of x cubed minus big F of 2x, and we're going to take the derivative of this. So derivative of big F becomes little f, just with an x cubed inside. Instead of it being an x like it was before, or a t, I guess it was a t, right, is what it's going to be in these problems you're going to see. It's getting replaced with an x cubed. And don't forget, though, from the chain rule, when we took the derivative, we know the derivative of big F, it just brings us back to the original function little f, because derivative and antiderivative cancel each other out. But don't forget, we got to do the chain rule, derivative of the inside. Then minus, same thing's going to happen over here. This is going to change back to little f, and times the derivative of the inside, so times 2. And there you go. So let's look at an example. So here we have a constant on the bottom, so we don't have to worry about the minus part. Just like we did here. Remember the constant on the bottom? When we took the derivative of that part there, it just ended up as 0. So we're just going to worry about the main part. What happens is we're going to take the derivative of the antiderivative. It's going to cancel out, leave us with the original function. We're just going to plug in the x squared and then multiply by the derivative of x squared. So here it's just 3x instead. So my answer is going to be this, square root, and you might have to watch this a couple times, honestly, minus, and then n for the t is going to be the 3x. And then times on the outside, 3. So the final answer with 3 square root of 15 minus 3x. Why the 3? Because of the chain rule. That was this whole part right here. That 2x I got earlier, derivative of x squared is 2x. So all I did was plug 3x into the t and then took the derivative of the 3x. I mean, I could do these all day. It's really simple. This one, it's going to be 3 times 2x squared. So I plug the 2x into the t, into both the t's actually. And then times the derivative of the inside, derivative of the 2x. That's the inside function. If you look up here, this is where we get a little abstract. The inside function, right? That one, the bound that we plugged in is the inside function. And so just kind of collect that. 2 squared is 4, times 3 is 12. And all of that's being multiplied by 2. So you get 24x squared plus 8x. And this just keeps on going. I mean, this is the most difficult one here. This is going to be, and it's nice that the lower bound's a constant. If the lower bound was something like 2x, you would end up subtracting that function from itself, just plugging in that 2x instead. So same idea, like if this was, let me go back to this example. Let's just say this was minus 2x here, right? Then we would have added minus, 3 times negative 2x squared plus 2 times negative 2 and then times negative 2. We would just put the minus there and then the same function just with the negative 2x plugged in instead and then chain rule it as well with the bound, chain rule the bound. Okay, last example here that I'm going to do. We're going to plug in that square root of x and then times the derivative of the inside. Derivative of square root of x is 1 over 2 square root of x. Square root of x squared, that's going to cancel out. We're going to end up with x over 2 square root of x. I would need to specify that x has to be greater than 0, but it wouldn't allow for this anyways there. So that would be your answer. I guess I could do this one. This would be sine of x cubed times 3x squared. So final answer 3x squared times sine of x cubed. So very simple. It's simple to do, but the main concept here might take you a little bit to look through this, watch this again or something and get the hang of that.